At T plus 0.678 seconds, the first warning appeared. It was smoke from the aft field joint of Challenger's right solid rocket booster. More smoke followed through the first 2.5 seconds of flight. Then it stopped. For the next minute, Challenger looked like a launch. The vehicle climbed. The callouts continued. The machinery of the mission appeared to be doing what it had done before. But the accident had already begun. The visible catastrophe came later, about 73 seconds after liftoff. By then, the public version could be told quickly. It was cold, the O-rings failed, and 7 crew members died. That version is accurate. It is also too small to explain why launch was still allowed. The smoke is the better starting point because it separates the consequence from the beginning. At 73 seconds, the chain became public. At less than 1 second, the chain became physical. Before that, the chain had already been organizational. The harder question starts before ignition. How does a warning stay visible in records, inspections, memos, charts, and meetings, then arrive at the final decision too weak to stop the machine? Challenger did not fail because the danger was invisible. It failed after a system learned how to keep flying with evidence that should have made flying harder. To understand how that happens, start with the promise the shuttle system had to keep. Mercury, Gemini, and Apollo were built around singular missions: dedicated hardware, dedicated risk, dedicated public attention. The shuttle was designed to break that model: reusable, frequent, routine, less expedition, more airline. That promise shaped the organization around it. When a program promises routine, every delay starts to mean something different. A scrub is still an engineering decision, but it is also a schedule problem, a budget problem, a public problem, a problem that moves through contracts, payload windows, congressional expectations, and the reputation of the agency. NASA entered 1986 with an aggressive flight schedule and a system that had to justify itself through repetition. The shuttle was not only a spacecraft, it was an operating model. The first thing to understand about Challenger is that the program was built to make spaceflight feel normal. Normal operation is useful. It is also dangerous when it teaches people to treat unresolved problems as background conditions. No one in this story needed to wake up wanting a disaster. That matters because the easy version turns the accident into a morality play. Bad people made bad choices, so better people would have stopped it. The record is harder than that. The system was full of people trying to do their jobs inside a decision structure that kept lowering the force of warnings. 3 pressures were running at the same time. First, technical uncertainty. The shuttle was enormously complex. Each flight produced new evidence about how hardware behaved in the real vehicle, under real loads, in real weather. That gap between design expectation and operating evidence is normal in engineering. What matters is how the gap gets handled. Second, schedule pressure. Delays did not move one item on one calendar. They shifted payloads, crews, customers, reviews, and promises. The cost of stopping was visible immediately. Third, institutional reputation. NASA was not only an engineering organization. It was a national symbol, a funding case, a Cold War instrument, and a public trust. These pressures met inside the same rooms. When they conflicted, the most flexible thing was often uncertainty. A technical concern could be reframed. It could be qualified. It could be moved to the next review. Schedule and reputation were harder to bend. So the practical standard drifted. The question became, keep flying unless the evidence against flying is overwhelming. That is very different from, do not fly unless the evidence for safety is clear. The difference showed up most clearly in one component. The shuttle used 2 solid rocket boosters for most of its thrust during the first 2 minutes of flight. Each booster was not built as one continuous piece. It was assembled from cylindrical segments, stacked and joined at the launch site. Where the segments met, there was a field joint. Inside that joint, Two rubber O-rings, a primary and a secondary, were supposed to seal the gap and keep hot combustion gases inside the booster. The joint had to seal quickly. Pressure inside the motor could distort the metal parts at ignition. The O-rings had to move into position fast enough to block hot gas before it escaped. Cold mattered because rubber does not respond the same way in cold. A seal that moves quickly when warm can respond more slowly when cold. In this joint, timing was not a detail. Timing was the safety margin. If the seals failed, there was no graceful backup. Hot gas could burn through the booster casing, reach surrounding structure, and turn a local leak into a vehicle failure. The O-ring problem had been showing itself before Challenger. Post-flight inspections found erosion on the primary seal. In some cases, gas had blown past it and left evidence deeper in the joint. Engineers documented the damage. They measured it. They reported it. The dangerous part is what happened next. Because the mission succeeded, because the vehicles came home, damage could be processed as evidence that the system had tolerated the condition. A damaged component in a surviving system can be read two ways. One reading says, "We were closer to failure than we should have been, so we stop and fix the condition before we repeat it." The other says, "The vehicle survived, the margin held, and the risk can be carried while improvement work continues." The second reading became easier each time the shuttle flew and returned. What had started as a serious anomaly gradually became part of the operating history. The O-ring warning did not disappear. It moved. That is how a warning can die inside a large organization. Not through silence, through translation. It starts when an engineer sees something wrong. The data is specific. The language is uncomfortable. Erosion, blow-by, heat effects, a seal that did not behave the way the design assumed. Precise evidence has force. Then the evidence becomes a discussion item. It enters a meeting with dozens of other concerns, other anomalies, other systems, other deadlines. The context broadens and the urgency flattens. From there, the discussion becomes a judgment call. Does this affect the next flight? The answer depends on the question the room decides to ask. If the question is, "Can we prove this will cause a failure?" the answer is usually no. Predicting a specific loss on a specific flight is hard. If the question is, "Can we prove this will not fail?" the answer is also no. But the first question keeps the schedule alive. Then the judgment becomes a schedule decision. The language changes again. It is no longer mainly about erosion depth or sealing time. It is about whether there is enough cause to delay. Delay has a phone tree. Delay has cost. Delay has a visible owner. If the flight succeeds, the decision becomes precedent. We flew with that condition and came back. That fact starts to compete with the warning that preceded it. This route ran more than once before Challenger. Each pass made the next one easier to defend. Engineers were not simply ignored, they were often heard, then absorbed into a process that had learned how to carry their concern without stopping. Months before Challenger, Roger Boisjoli warned that a similar field joint problem could lead to catastrophe of the highest order and loss of human life. That memo did not come from hindsight. It came from inside the system, before the accident, from an engineer close to the hardware. The temperature pattern also had more weight than the launch night argument made it feel. When the full flight history was framed one way, the cold weather signal could look debatable. When the full record was framed another way, cold O-ring distress became much harder to dismiss. A chart can contain real information and still weaken the warning if it frames the wrong question. Richard Feynman's later appendix named the broader danger plainly. Previous success can become misleading evidence. A survived flight can show that the vehicle got through. It does not prove the risk was safe to repeat. By January 1986, Challenger was not facing a new problem. The program had evidence of O-ring distress. It had temperature concern. It had waivers. It had memos. It had a known field joint problem. It had a launch system that kept treating survival as part of the safety case. Then the weather turned that old problem into a launch decision. January 27th, 1986. Less than 24 hours before the scheduled launch. A teleconference connected NASA's Marshall Space Flight Center, Kennedy Space Center, and Morton Thiokol, the contractor that built the solid rocket boosters. The subject was temperature. Forecasts and engineering estimates pointed to launch conditions far colder than prior shuttle experience. The launch temperature would be about 36 degrees Fahrenheit. The right aft field joint was estimated colder, around 28 degrees Fahrenheit, plus or minus 5 degrees. Thiokol engineers were concerned because cold could slow the O-rings at the exact moment they needed to seal. Their recommendation was clear. Do not launch below 53 degrees Fahrenheit. That number mattered because it was tied to the lowest relevant prior experience they believed they could defend. NASA managers pushed back. In a technical review, pushback can be necessary. The danger was the standard that began to govern the room. The question drifted. Show that this is safe to fly became prove that it will fail. That shift reversed the burden of proof. Instead of requiring evidence that launch was safe, the process demanded evidence that failure was certain. Engineering evidence usually does not arrive that way. It arrives as a missing margin, a condition outside experience, a trend with enough signal to matter before the catastrophe supplies certainty. The engineers had evidence of risk. They did not have an equation that converted temperature into guaranteed loss of vehicle. That absence became useful to the launch case. Thiokol asked for an offline caucus. The caucus lasted far longer than the 5 minutes first requested. When they returned, the recommendation had changed. The new position was that the data was inconclusive and launch could proceed. The cold had not changed. The joint had not changed. The limits of the data had not changed. The decision frame changed. One instruction from that caucus still carries the shape of the moment. Jerry Mason told Bob Lund to take off his engineering hat and put on his management hat. No single phrase explains the disaster. No single person explains it either. The deeper fact is that the same process could take a specific engineering objection and return a launch recommendation from the same evidence. The launch eve reversal is dramatic, but it is not the whole failure. A warning also has to travel. It has to move from hardware to engineers, from engineers to managers, from contractors to NASA, from lower review levels to the people with authority to stop the launch. At each step, the signal can be compressed. Compression is normal in large programs, but when compression changes an active objection into a resolved item, the system has made a decision without naming it directly. Safety should have been a backstop. The Commission later criticized weak problem reporting, inadequate trend analysis, misrepresented criticality, and safety structures that did not give the concern enough independent force at the decisive points. People can care about safety while the way decisions are made still lets a warning arrive too late, too thin, or too resolved to change action. By launch morning, the warning had passed through hardware evidence, paperwork, meetings, waivers, charts, recommendation, caucus, and management acceptance. At the end of that route, launch was still open. At 11:38 a.m. Eastern Standard Time on January 28, 1986, Challenger launched from Kennedy Space Center. Within the first second, smoke appeared near the right aft field joint. The primary O-ring had not sealed the way it needed to seal. The secondary O-ring, affected by cold and joint movement, had not saved the joint in time. The smoke continued through roughly T plus 2.5 seconds. Then it disappeared. The Commission considered that combustion residue may have temporarily sealed the breach. For a short time, the vehicle could look normal while the failure chain remained alive. That temporary quiet is one of the clearest details in the record. The physical system did what the organization had been doing for years. A sign of breach appeared, an explanation arrived, and flight continued. Around 58 to 59 seconds into flight, flame became visible again. Hot gas from the right booster began damaging surrounding structure, including the external tank area. At approximately 73 seconds, Challenger broke apart. Francis Dick Scobie, Michael Smith, Judith Resnick, Ellison Onizuka, Ronald McNair, Gregory Jarvis, and Krista McAuliffe were lost. The visible failure lasted seconds. The invisible one had been accumulating for years. What came next was the question every institution fears. How did this happen when the evidence already existed? President Reagan appointed the Rogers Commission, chaired by William Rogers. Richard Feynman was one of its members, and his independent work became part of the public memory of the investigation. The physical cause was direct: failure of the seal in the right booster's aft field joint, hot gas escaping, damage to the external tank area, and vehicle breakup. The commission did not stop at the physical cause. It found a flawed launch decision process. It found communication failures. It found that crucial information about O-ring history, temperature concern, and continuing engineering opposition did not reach key decision makers with the force and clarity it needed. The people closest to the hardware had the sharpest version of the risk. The people with the authority to stop launch received a softened version of it. The commission described the immediate failure, the part, the launch decision, and the communication system that softened the warning. Diane Vaughan later named the larger pattern the normalization of deviance. A deviation from expected performance becomes normal because the system keeps surviving it. The phrase is useful because it does not require a conspiracy. It describes a slow adjustment in what feels acceptable. The line moves because each previous crossing did not end in catastrophe. Challenger is taught in engineering programs, business schools, and organizational behavior courses because the pattern is not limited to NASA. Repeated near misses create false confidence. Every time a system survives a close call, perceived risk can drop. The near miss gets counted as validation instead of warning. Missing data gets mistaken for safety. No evidence of failure is not the same as evidence of no failure, especially when the dangerous condition has not really been tested. Schedule pressure changes proof standards quietly. No one has to announce that the bar has moved. The bar for stopping can rise inch by inch until only certainty of disaster justifies delay. Institutions reward continuity over interruption. The person who keeps the line moving is easier to celebrate than the person who stops it for a risk that might never become visible. Anomalies become background noise. The first time something unexpected happens, it gets attention. The fifth time, a tracking number. The 10th time, it starts to sound like how the system works. These behaviors appear wherever the cost of stopping is immediate, and the cost of continuing is statistical. Healthcare systems, financial systems, infrastructure, software. Any organization that has to decide whether a warning is strong enough to interrupt momentum. Challenger did not invent this pattern. It made the pattern visible. Disasters rarely begin at the moment of impact. They begin when a system gets used to explaining away what it should have stopped to understand. Challenger was a long sequence of accommodations, each one easier to defend than the whole chain would have been. The smoke at T plus 0.678 seconds is why the story should not start with the explosion. The first visible warning was small. Then it vanished. For a while, everything looked normal. The same thing had already happened inside the organization. A warning appeared. The system explained it. The launch continued. Next time, another design failure, another system that taught itself to ignore what it already knew.
Specificity and rank define the order, but fragile architecture can't hold water. It's a cascade of forgotten code, heavy legacy begins to overload.